So we have done with the common emitter amplifier. We have looked at gain, input and output resistance, swing, lower and upper cutoff frequency here. And last lecture we were looking at some of the trade-offs and limitations of common emitter amplifier. And one of the things that I was pointing out in the last lecture was that when you look at an amplifier like this, the supply voltage affects almost all the characteristics. For example, we saw that the drop here across the collector resistance here determines my gain. And for example, if I would like to increase gain, one of the ways of doing it is by increasing GM. You know, gain is GM times RC parallel RL. And the way to increase GM is increase the collector current. And as you increase the collector current, the drop increases. Okay, so you can see clearly here, the voltage drop here determines the gain. And the drop here, we don't want the transistor to enter into saturation here. So VCEQ that you see here has to be larger than the swing that you're interested in. So the drop here has to be larger than the swing here. So this drop is related to swing. And this drop we have seen earlier is related to the stability part here. You know, we've included RE to ensure that bias point is stable against variations in beta. And so we want this drop to be of sufficient magnitude to ensure stability here. And so the supply voltage, then if we look at the budget here of supply voltage, you know, you have to allocate some amount of supply voltage here, some amount of it, some fraction of it here, and some fraction of it here. And now the trouble that comes is if I want to build up large gain, then we know that this drop has to be sufficient. And in many applications, I may not have a supply voltage which is sufficiently large. For example, this particular calculation will immediately show you that if you want a gain of 100, then this drop has to be larger than at least 2.6 volt. All right, so 2.6 volts. So if you're running your, building your amplifier on 1.5 volt battery, you don't have that much voltage available here. So the problem that this particular analysis is pointing out is, suppose I want a high gain without, and I don't have enough supply voltage. How do I do that? Okay, so that's the problem that we are addressing. So the issue is, how do I get large voltage gain without requiring a large supply voltage? All right. Now, so the way to proceed is, so that's the problem here. So we said in the last lecture that, you know, since we are talking about drop here, why not replace that particular element by some other element? Okay, because we don't want a drop here across this particular element to be large. And so if we want to change this particular characteristics, we have to look for some other element here. Instead of RC, suppose we put an element X here. And if we do a small signal analysis of this one, remember all elements are replaced by their small signal model here. And so element X, which is a two-terminal element that you see here, I will replace it by a small signal model, which will be equal to Rx. Any two-terminal device, as I said, under low frequency condition can be modeled as a resistor. And therefore, this one is nothing but Rx. And the gain that you will get is, if you look at this equivalent circuit here, so VBE is equal to Vs. And so we have a current which is GM times Vs. And this current flows through a parallel combination of resistor Rx and RL here. So gain will be less than GM times Rx. So if we are replacing the collector resistance by a new element X, what we are looking for is an element which will give us large value of Rx, because we want large gain. Large value of Rx, but at the same time, the element X should be such that the DC drop across it is small. All right, so going back, we are looking for this element X such that a small signal resistance, Rx is large, and the drop across this particular resistor, DC drop, is small. That's the kind of an element that we are looking for. And one of the possibilities is a transistor. If you look at a transistor here, suppose I take a transistor and I bias it here at this point. Now, if you look at the voltage drop, the DC drop here across the transistor, you're seeing here something like a volt. 1 volt here is a DC drop across the transistor. So the drop is small. But look at the resistance of the transistor here. Resistance is what? The change in current with respect to change in voltage. That's the small signal resistance here. You see that this characteristic is flat, which means that the conductance is small. Conductance is small, and therefore the resistance is very large. So here is an element, if you think of transistor itself and you bias it in the active mode, you find that it has a large small signal resistance. Small signal resistance is always derivatives, change in current with respect to voltage here. So it's the slope here. It's the slope here. So you see that it has a large small signal resistance, but very little DC drop here. So the idea is, why not replace the element X by the transistor itself? Okay, and then we'll have small voltage drop, DC drop here. So we'll solve a problem that if we replace RC by a transistor, the voltage drop across it is going to be small, DC drop 1 volt. While when I look at a small signal equivalent circuit, I will get a large value of a resistor here, and therefore I'll be able to get large gain. So that's the motivation for replacing the resistor by a transistor. Now, there are various possibilities of doing it. Suppose I do it like this here. I take a transistor, and till now I was talking about a transistor as a 2-terminal device. I mean, in this case, right? I was saying element X is a 2-terminal device. Transistor is a 3-terminal device. So one may think, well, why not take base and collector and short it together, and I get a 2-terminal device here, right? And so replace RC by a transistor with this base collector shorted together, right? Now, if you do that, you can do the small signal equivalent circuit here. And so what happens is, again, current. So this is a simplified amplifier here. We have not shown biasing explicitly. We've just said is bias at a, using a 10 microamperes current here. And so when you build a small signal equivalent circuit, the capacitor, of course, gets shorted here. Current source is open. And so you get this transistor. We have to replace it by its hybrid pi model here. The other one, transistor, is over here, Q2. VCC, we know, becomes ground here. So that's a ground here, and this is a ground here, and we have an RL connected here. So now what we have to do is replace each one of them by their hybrid pi model here. So this Q1 becomes R pi GM times VBE here. So that's Q1 is over here. And it's easy to show here that if you look into the emitter here, if you look into the emitter, what do you see? We've already seen a case when you look into the emitter, what is the resistance that you see? R pi plus whatever is the resistance in the base divided by beta, right? So we don't have any resistance in the base. RB is 0. R pi divided by beta is nothing but 1 over GM. R pi divided by beta is 1 over GM. So when I look at this transistor here, the transistor basically behaves as an element with the resistance equal to 1 by GM. In the low frequency region here. High frequency, of course, there'll be capacitances and all that here. All right. So 1 by GM, and RL, of course, is there. And therefore, what happens is now I can easily calculate the gain. So this is the result that we've used, R pi by plus RB divided by 1 plus beta here. Note that resistance looking into the emitter is small. R pi plus RB 1 by beta here. Resistance looking into the collector is large. Now, you can see the trouble. We have not used the transistor properly because we wanted an element here which had a large resistance, but we have connected it in this particular manner so that what happens is, at this point, I'm looking actually into the emitter here, and therefore I get a very small resistance. 1 by GM, if you do a calculation, let's say a transistor is biased at 1 milliampere current, GM is VT by IC. So VT by IC means, GM is IC by VT and 1 by GM is VT by IC. So VT is 26 millivolt, IC is 1 milliampere. So you get 26 ohms. So you are getting here a 26 ohms. And we were wanting a very large resistance here. So this is not the way to connect a transistor here. We want to replace RC by a transistor, but not in this way. And neither can we connect. So the idea is a transistor offers a large resistance when you look into the collector, at the collector node. I can't connect it obviously like this because this implies that the current is flowing up and while I want the current to flow down. So I can't do that here. A natural solution is a PNP transistor. If you want to replace your RC here by a transistor, a PNP transistor here. When you do that, this is my PNP transistor. I have to apply some voltage to bias it. Let's not worry about it, how to apply this for a moment. Now, if I build this equivalent circuit, this part I know. And now here, remember what will happen is this transistor, what will happen is that when you draw a small signal circuit, you will have this node, this will be ground, and this will be ground. And therefore, this transistor, as you can see here, ground, and when you look into the collector, you see an R0 here. So what will happen is, in the small signal circuit, you'll replace Q2 by a resistor R0. And R0 is a very large resistor. It's a very large resistor, and therefore the gain of this particular transistor will become very large. And remember, all that I have to do is keep transistor Q2 in active region. And all I need is the emitter to collector voltage has to be larger than some 0.5 or 0.2 or so. So I have a very small drop across the transistor here. All I need is maybe a 1 volt or so, depending on the swing. And the resistance offered by Q2 will be very large. Resistance at this particular node will be very large. So I'll get very high gain without requiring a very large supply voltage. So now if you look at this particular amplifier, if I have, let's say, 1.5 volt battery, I could have 0.75 volt here and another 0.75 volt here. And the amplifier will work, and I can have very high gain depending on the value of R0, how I bias it. So there's possibility now, once you replace the resistor by a transistor, there's a possibility of getting large gain without requiring very high supply voltages. Okay. So that's one solution. We'll look at it in more detail later on. The other solution that one of you suggested was, instead of RC, why not replace it by an inductor? Inductor is an element. DC drop is 0. And when I look at small signal, and especially if my small signal is an AC, then we know that inductor offers a impedance omega L. And all I have to do is choose a sufficiently large inductor omega L, which is, so that this omega L becomes very large here. Suppose RL is 1K. All I have to do is omega L is much, much larger than 1K. So in principle, I can do it, except that, let's say the frequency is 1 kilohertz, RL is 1K. It requires an L of 1.6 henries. And if you know how the size of the inductor increases with the value, you'll know that 1.6 henries is a very large inductor. So it will occupy it will become bulky, and so that's the price that you have to pay. Further, inductors are something that you can't make on an IC, so solution is not feasible if you're doing a IC amplifier here. Okay, but it's a potential solution. It used to be very common. If you go back and look at earlier radios, if you look at earlier radios, pocket radios that used to be there, and the circuits used to be discrete. If you go and look at it, this is an example of an AM radio receiver circuit here, and you see you don't see anywhere a resistor, because you remember the radios had to run on 3 volt or these are portable devices. Voltages were small. You don't see any RC here. They use a lot of transformers and inductors. And so this was the solution that was used. It was very common solution at that particular time. So inductor or a transformer was used to couple the signal onto the load here. Okay, so this allows you to use low supply voltage, at the same time get high gain. Okay. So we are looking at various problems with the circuit. Another problem which is of similar kind. If I look at swing depends on these two factors here. So this equation is important for tomorrow as well. This is determined by saturation, that I know my maximum voltage swing is either one of the two, whichever one is smaller. VCEQ minus VC sat. This is from saturation, and this is from distortion. And if you look at these expressions here, getting large swing implies, of course, you have to get large VCEQ. And also, it requires that you have large value of ICQ, RC parallel RL. Both these quantities have to be large. And both of them are implying large drop, large supply voltage here. Okay. And if you look at this term, there's nothing you can do. If you want a 2 volt swing, you will have to put a supply voltage, enough supply voltage so that you can make VCQ equal to 2. So you can't do anything about it. While the other term, ICQ, RC parallel RL, you have to make this also large. Now this one, if I look at RC parallel RL, the same solution helps us. If we replace RC by a transistor, then we get, instead of ICQ, RC parallel RL, we'll get ICQ R0 parallel RL. So if you replace your resistor by a transistor, you solve this particular problem, because you are able to get a large value of this term without requiring a large supply voltage. So the solution that we talked about earlier, that replaced the resistor by a transistor, helps us even here. Okay, but this part will require a larger supply voltage. You can't do anything about it. The other one is, if you look at this particular term here, this term is coming about because of distortion. And distortion is coming about because we have our transistor behaves as a nonlinear device. Okay. And so another way of counteracting that particular problem is by improving linearity of the amplifier using negative feedback. I'll illustrate in a minute how negative feedback helps us to increase the linearity here. How do I implement negative feedback? Very simply, what I do is, whatever value of RE that you see I have put here, this RE was put in order to ensure bias point stability. All I do is I break RE into two parts, RE1 and RE2, and a part of RE, I leave it unbypassed. A part of RE is not bypassed, and a part of RE is bypassed here. Now what happens is, when I had put a CE across the whole of RE, my RE was not playing any role under small signal condition. This RE was getting shorted here. Now, if I draw a small signal circuit, RE2 will get shorted out, but RE1 will appear in my circuit, small signal circuit. And RE1 acts as a negative feedback here. So, you can see here how it acts as a negative feedback. So let's say collector current increases. For whatever reason, collector current increases. If that happens, the emitter voltage here, small signal emitter voltage will rise. As emitter voltage rises here, base emitter voltage that you see here between these 2 points will fall. And as base emitter voltage falls, IC falls. IC is related to base emitter voltage here. So you can see a negative feedback operating here. So the moment you put an RE1 in the emitter, you have a negative feedback operating. And the larger the value of RE1 that you put, the stronger the negative feedback. Okay, so that's how you that's one way of putting negative feedback under AC condition. Under DC condition, we had already put negative feedback using R. Under AC condition, all you do is a part of it, leave it unbypassed. And now you have negative feedback under AC condition also. Now, how does a feedback improve linearity? Okay, so let's, this is a diagram that I'm sure all of you have seen in control systems. We have a system here, and we put a feedback. This is a feedback network. This is an input here, and this is the feedback signal, and that's an error signal. And based on that, you know that very simply you can derive that the closed loop gain, this is the open loop gain here, and the closed loop gain is AF is equal to A by 1 plus A beta. Okay, very simply, SFB is equal to S naught multiplied by beta. You subtract it, write down error signal here. Error signal gets multiplied by A. So it's a very simple derivation, which says that the closed loop gain is A1 by A plus beta here. Now, when we're talking about nonlinear, we are saying this system is nonlinear. My amplifier is nonlinear, right? And I'm putting a negative feedback to make the overall system linear, which means the closed loop gain, the closed loop system becomes more linear as compared to an open loop system which is nonlinear. Okay, so let me show you an example here. This is a hypothetical example. Let's say I have an amplifier like this here. This amplifier that you see is here shown here, V0 versus Vin. So there's a slope here of 2 times 10 to the power 3, and there's a slope here 10 to the power 3, right? Obviously nonlinear, but it's piecewise linear. But that's not important. The important point is I have a nonlinear amplifier. And the nonlinearity you can see here. Gain is something here, and gain is something else at a higher input here. So I have a nonlinear amplifier, and suppose I put negative feedback here. So what kind of a negative feedback do I put? I put a beta of 0.1. Okay, I put a beta of 0.1. So closed loop gain will become A divided by 1 plus A beta. And now I have a closed loop gain, so I plot it. And look at the closed loop gain, V0 versus Vin. Linear. Earlier it was like this, note here. You can see nonlinearity, and you can see here it's linear. I put negative feedback, and my characteristic V0 versus Vn becomes linear. Why is that? Why is that? Because of the dominant role of beta. Yeah, you know that from this expression that if my feedback factor A times beta loop gain is sufficiently large, then what happens is this becomes A by A beta, which is simply equal to 1 by beta. 1 by beta. And therefore it becomes more and more independent of A. And that's what is happening here. The gain here is 9.9 and the gain here is 9.95. The characteristics is highly linear. So I had an original amplifier which was nonlinear. I've put negative feedback and I've made it linear. Now, is that a good solution? Yes or no? What did you lose in the process? You lost the gain, right? So you had a gain of how much? 1,000 and 2,000 earlier. You had a gain of 2,000 here and you had a gain of 1,000 here. But it was nonlinear. And now you have a gain of 10. But you have highly linear characteristics. Okay? So this is one of the things that feedback allows you. At various places you will see that one uses negative feedback. And what one does is you build up gain. You have multi-stage amplifiers or whatever, you build up gain. And then what you do is, if you're interested in input traces being very high, you sacrifice gain and you'll get input traces. Or you can sacrifice gain and you can get linearity. You can sacrifice gain and you can get output traces if you want. You can sacrifice gain and you can get bandwidth. Alright, so negative feedback allows you to do this trade-off. Build up large gain and then sacrifice gain to get other things in return. Okay, so this is showing you large gain is being traded off to get a highly linear characteristics. Okay, so that's the strategy that you can use here. So look at this particular case here. This is the amplifier. The screen is smaller, so I don't know if you can see the values here. In the emitter, we have a 510 ohm total resistance of 560 ohms. In the emitter, total resistance is 560 ohm. And what we have done is, most of the emitter resistance is bypassed. We have left only 50 ohm in the emitter here. Okay? And as a result of it, I get a characteristics which is much linear. A 50 ohm resistor allows me to get a fairly linear characteristics with harmonic distortion less than 2%. Okay, I'll show you some comparison here. Look at this one. Both amplifiers are identical as far as biasing is concerned. 2.2K here, 2.2K here. 22K, 6.8K, exactly the same. Biasing wise, DC wise, exactly same. All that here is 0.56K emitter resistance. Here also total emitter resistance is 0.56K. All that we have done in the second case is left 50 ohms unbypassed. And now you can compare the characteristics. So bias points are the same. 3.4 milliamperes, 2.57 here. Same here on this side. Now, gain on this side is 110. And because we have put negative feedback due to 50 ohms, what we have done is we have sacrificed gain. It drops to 18.2. So gain is being sacrificed from 110 to 18 by a factor of 5 or so. And note the advantages that you get here. Rn is 0.82K here. Rn becomes 2.7K here. Input resistance is increased. Output resistance is determined primarily by this resistor here, 2.2K and 2.2K. It remains the same. Now note something interesting. Here, output swing is 0.39 volt at a harmonic distortion of 2%. Very small output swing here. The output swing, you get 2 volt at a same harmonic distortion of around 2% here. So my amplifier is much more linear. I'm getting 2 volt swing at 2% harmonic distortion, and all I could get is 0.4 here. So much linear characteristics here. Lower cutoff frequency was 1.67 kilohertz here. Lower cutoff frequency is 0.3. I have an improvement in lower cutoff frequency. Upper cutoff frequency was 5.8. Upper cutoff frequency is 26.46. So you can see here what a 50 ohm resistor can do. All that we have done is a part of very small fraction of emitter resistance, and what we have done is left it unbypassed. Very small resistance here and unbypassed here, and what it does to my characteristics. Okay, so this is the summary here that you can see. So negative feedback we have put, and what we have done is you can see here we have sacrificed gain by a factor of 6, and input resistance increased by a factor of 3.3. Swing, note here, has increased by a factor of 5. Lower cutoff frequency became smaller by a factor of 5. Upper cutoff frequency became almost larger by a factor of 4.5 here. So in general, approximately the factor by which you lose the gain, you get something similar factor of improvement in many other characteristics. You get improvement in Rn, you get improvement in swing, you get improvement in FL, you get improvement in FH. So it's a very powerful technique, negative feedback, incorporating it in amplifiers and achieving characteristics which you could not have achieved otherwise. Directly achieving 2 volt swing at 2% harmonic distortion would have been very difficult for you directly. from a single stage amplifier. But using negative feedback, one can do that. Okay, so extremely powerful way of, yes. How is? Rn is improving. Okay, so the results are not shown, but what happens is, if you look at Rn is a resistance looking from here. And what you see in Rn are two things. One is this Rb that comes in, and the other one is resistance looking into the base. And when you look into the base, here what you see is R pi, because this node is ground. This node is ground here, so all you see is R pi. When you look in here, you see R pi, plus you see 50 ohm resistor in the emitter. And that 50 ohm resistor in the emitter gets multiplied by the beta. So 50 gets multiplied by beta and adds to it. Okay? So 50 multiplied by 100 gives us how much? Gives us 5K. So this 50 translates into, when you look from here, 5K resistor here. And that is what is causing this Rn to increase. Okay? So that's why many times when you see common emitter amplifiers, you will not see people bypassing the whole of it. You will always, in general, you will find people leaving a part of Re unbypassed to achieve swing here, to achieve better input resistance, and you know, all of these characteristics here. You could leave 50 ohms. If you don't want to sacrifice gain so much, you could perhaps leave 20 ohms unbypassed. And 20 ohms will also result in improvement here. Okay. All right, so that's one problem. We saw a strategy of using negative feedback to obtain improvement in several other characteristics here. The other one is, note that when you look at input resistance, you see R1 parallel R2 coming along with R pi here. And so an issue is there a way of eliminating this RB? Why? Because if you look at my drop here, VE, the voltage here, VE depends on XB, and XB is given over here. XB is RB divided by R pi. So if you want a large input resistance, what you would like to do is make this RB here, R1 parallel R2, let's say 10 times or 50 times larger than R pi. Now, as you do that, RB, as you make it much larger than R pi, this factor XB becomes large. And XB goes and affects the value that you have to ensure for emitter voltage here. So emitter voltage becomes large. And you don't want emitter voltage to be too large, because then it takes away the voltage drop that you can get across the collector emitter and all of that. So the issue is, why not just eliminate R1 and R2? Why not just get rid of, why bias it from this side like this here? Why not eliminate R1 and R2 altogether? Okay. Now, if I eliminate R1 and R2, well, I need a certain amount of base voltage to bias. How do I do that? Well, a very simple solution is eliminate R1 and R2. And all that I needed was a voltage, sufficiently large voltage from this side. But you know that instead of applying voltage from one side, you can apply it from the other side here. So what you do is, instead of applying a positive voltage here, you apply a negative voltage from this side. So that's a possible solution. Get rid of R1 and R2, make a negative supply here, and use an RE, and then bias it from here. Is there a problem with this circuit? Will this circuit work? This could have been a good quiz problem. Will this circuit work? Will it give me any gain? I mean, you know, put 5 volt here, minus 5 here, RC, RE are all reasonable. Let's say they're all reasonable values. This circuit will never work. Why? What is the first thing you have to ensure for a transistor, for a amplifier to work? Forward active mode. When you do DC analysis, what will happen to the base terminal? Capacitor means open circuit, base current is 0, collector current is 0, is in cutoff mode. So this is not going to work. I have to provide a path to the ground here. Okay. So, this circuit is wrong, and you need to put something here. In fact, what you could do is, so one way is, as I said, put something here, a path to the ground. But even better solution will be simply remove the capacitor. If you simply remove the capacitor and directly connect Vs here to the base, when you do a DC analysis, what will happen to this? It's like a ground, and so the transistor is biased properly. And under AC condition, the signal is anyway going into the base. So all you need to do is just remove CB here, and it will go directly into the base here. And then, of course, depending on how you choose RE, you can get a particular value of current here. Okay. But the problem, of course, is that it requires another power supply voltage here. You require a dual power supply, positive here and negative here. There are other issues as well. The other issues are, you can see, when you make an amplifier, we have said what you require is that the swing that you see here should be rail to rail. Rail to rail meaning that on the positive side, it should start approaching VCC, and on the negative side, it should approach VEE. It should approach VE. Rail to rail swing is one of the requirements that we have. And later on, we'll see that efficiency of an amplifier, goes down as the output voltage swing departs from rail to rail, kind of a feature here. But here now note, if I have an amplifier like that, what is the value of this particular node? Imagine the capacitor is not there. DC value is minus 0.7. This value is minus 0.7. Okay. Now we have seen when we look at swing, that swing can, if I have a collector voltage, swing can only go as low as VE, emitter voltage here. And emitter voltage is only minus 0.7. So on the negative side, my swing could only go to minus 0.7. While I may have used a supply voltage of minus 5 or minus 12. So my negative swing is very bad here. All that I will get is minus 0.7 here. Okay. And so this negative swing is an issue. And, that's the price that you have to pay. Now, a way to improve the negative swing is, if you look at this diagram here, if you want to improve the negative swing, you want to take VE here and push it down. Make VE smaller and smaller, go towards the negative power supply here. How do you push VE down? How do I push VE down? Changing RE and all that will not do. So remember, the drop from here to here is 0.7. So if you want VE to go down, you want base voltage to go down. And how will you make base voltage go down? Well, if you add a resistor here from here to ground, maybe you can make it base voltage to go down. But then if you add a resistor, remember RB, our whole purpose was we didn't want an RB. We didn't want a resistor in the base here because that was affecting our original purpose here, which was to keep VE small here. So it's not as simple to eliminate RB and eliminate the voltage drop here. So you have all these issues that are there. Okay, so I just wanted to point that out. All right, among the various trade-offs, this is another interesting trade-off which is there here. Okay, look at the lower cutoff frequency. We said lower cutoff frequency is primarily determined by, under most cases, by the emitter bypass capacitor here, which is given over here 1 by CE, RE parallel and all that term here. And in many cases, what will happen is that this term, R pi by beta, may turn out to be a dominant term here. And therefore, omega L, I can write it as beta by CE into R pi by beta. Especially if my RS is negligible. RS is negligible here, then I'm left with R pi by beta here. And RE very often is, we can show it also, RE will be much larger than R pi by beta under most cases here. So my lower cutoff frequency is beta by CE into R pi. Alright, Rin we know is R pi parallel RB, and therefore I can approximate it as R pi, keeping in mind that RB is larger here. And using these two equations, we can say omega L into Rin is beta by CE. Okay, so beta is a constant, and emitter bypass capacitor is also a constant because I can't keep on using larger values because capacitors become bulky here. Okay, so if right hand side is a constant for you, then what it says is there a trade-off? Is there a trade-off here or not? Yes, how? You want a smaller value of omega L, correct? A smaller value of omega L implies a larger value of Rn, which is very good. I want smaller omega L, I want larger Rn. Okay, so how is that a trade-off? It's not a trade-off. You're getting all, good stuff from here. Lower omega L, higher Rn. But the problem is, we have seen this one here. AV Rn by R0 must be less than beta. Now you can see a trade-off. If you try to improve your omega L, make it go down, you'll have to increase Rn Fine, you have to increase Rn. So if you want to improve it by a factor of 10, Rn has to go up by a factor of 10. If you increase Rn by a factor of 10, what do you have to do? Maybe you have to sacrifice gain by a factor of 10. Or you have to increase output resistance by a factor of 10. So now you can see the trade-off. You try to improve this one, you have to improve this one as well then. And once you improve Rn, then you sacrifice AV or R0. So you can see I can take these equations, I can write it in this manner here. And now you can see here that gain and lower cutoff frequency can be traded off. If you don't want to touch R0, then if you try to reduce the lower cutoff frequency, the gain also gets reduced. They're linearly related here. Okay, so this is one instance of gain bandwidth product that you see. So you can see how things are related together. Omega L will require Rn change. Rn change, if you don't want to change R0, will require a change in AV, a downward change in AV. Okay. So gain bandwidth trade-off. This is a problem which is very important, especially if you want to make amplifiers on an IC, on a silicon chip. This uses a lot of capacitors here, CB, CE, and CC. 3 capacitors that you see here. And all these capacitors have to be of large magnitude. You know, you can do a very simple calculation. You want a lower cutoff frequency of 100 Hertz. Resistors are in the range of kilo ohms. And therefore, what value of capacitor do you require? Immediately it will tell you in microfarads. Now, here is the trouble. How do you make capacitor on a silicon IC? You do it using the following way. One very common way of making a capacitor is, you know, a capacitor is a dielectric sandwiched between 2 plates. So one of the plates is a metal. Another dielectric is your silicon dioxide. And another plate that people use is silicon itself acts as the other plate of the, you know, especially if you dope silicon to very high levels, this acts as the other plate of the capacitor. So if we do a very simple calculation, capacitance of a parallel plate structure is epsilon by T oxide multiplied by area. Silicon dioxide dielectric constant is 3.9, and this is the free space permittivity. I've taken a typical value, let's say, of silicon dioxide thickness, which is 200 angstrom, 20 nanometer. And then, of course, it depends on the area. If I do a calculation, 10 microfarad capacitor requires an area of 57 centimeters square. Your whole silicon IC has to be a millimeter or a centimeter by a centimeter. You know, even the most powerful, you know, Pentium chips or with 4 cores and all that will be a few centimeters by a few centimeters. A 10 microfarad capacitor is requiring a 57 centimeter square area, which clearly shows large capacitors you cannot make on an IC, on silicon. These are not possible. Even nanofarad capacitors will give you a very, very large, unacceptably large area. You can't do that. Okay. So large capacitors are out of question. So if you were to make an amplifier like this on a silicon IC, I can't make CB, I can't make CE, I can't make CC. Now, if you can't make any of these capacitors, then this particular circuit will not work. And we have to, because if you don't use a capacitor, if you simply short it, you know that VS will short my R2, transistor is no longer biased properly, I don't get any gain. So that's the problem that I'm trying to point out to you, is how do I bias without using any of these capacitors here, okay? And that's the solution. So this amplifier then is not suitable for an IC. You can't build it on an IC. Nobody builds a common emitter amplifier on a silicon chip using a structure like this. This, I said right in the beginning, is a structure that you use for a discrete implementation. On a PCB where you have all these discrete capacitors and resistors, you use it in that condition. On an IC, we'll see you use a very different approach for building a amplifier. The other one, we have already seen upper cutoff frequency. We have a slightly complicated expression. This is the time constant associated with the output part, and this is the time constant associated with the input part here. We have C pi. C mu gets multiplied by Miller's effect, the gain here, GMRC dash here. With a little bit of manipulation, you know, defining gain as, in fact, this is not required here. You can, GMRC dash is proportional to the gain here, and you can very easily see here you don't have to go into this expression, that as I increase the gain, I increase this particular part here. So two ways in which gain and bandwidth are related together. One is, note that gain is GM times RC dash. So as you try to increase the gain, you increase this particular term. And therefore, my bandwidth goes down. The other way is, many times we increase the gain, not by increasing GM, but by increasing RC. So as you increase RC, even this term goes up here. And therefore, bandwidth and gain are inversely related together. Now, one of the biggest trouble is this particular term. This one here. Because this term, if you note here, this is C mu multiplied by RC dash, and this is C mu multiplied by this one. This term is usually much larger than this one. Okay? And therefore, what is bothering us, in this gain bandwidth product is this term. And where does this term come? From Miller's effect. If you recall, we had a capacitor connected between input and output, C mu, and that got multiplied by the gain. And this is what is bothering us here. So gain bandwidth is showing you. If I try to increase the gain, bandwidth keeps on going down, upper cutoff frequency. For some typical numbers here, this is the graph that is shown here. So the idea is that this term then is coming about because of C mu. Now the issue is, how do I get rid of Miller's effect? Every time you have a Miller's capacitance connected between input and output, remember, I'm not talking about common emitter amplifier now. I'm talking about any amplifier in which if you have a capacitance connected between input and output, that capacitor will always get multiplied by the gain. And therefore, as you increase the gain, that capacitor will appear as a very large capacitor when you look at it from the input side. And that will affect my bandwidth. So now if you're looking for a way to avoid this one, what you're looking for is an amplifier in which there is no capacitance between input and output. That's what you're looking for. In a configuration of an amplifier in which you don't get a capacitance between input and output. Can we get such a configuration? Well, look at this transistor here. You have a capacitance between emitter and base. You have a capacitance between base and collector. How do I build an amplifier such that between input and output, I don't get a capacitance? Is there a solution here? Huh? Between emitter and base I have. Between base and collector also I have. So now remember, when you build an amplifier, where should I connect the input? What are the possibilities? If I connect the input here, say at the base, input is going into the base and output is coming from the collector, I will get a capacitance between input and output. If I connect the input to the emitter, can I take the output from the base? It doesn't make any sense. You should try it out and see whether it makes sense to take an output from the base. If you connect the input to the emitter and take an output from the collector, is there a capacitance between emitter and collector? No. Alright. So, no capacitance between emitter and collector. So, it's pointing out to a possibility of what we call as common base amplifier. Look at this circuit here. It's the same transistor that we have seen earlier, biased in exactly the same way. I have R1, R2, RC, RE. It's just, rotated 90 degrees. Now what we do is, we apply input to the emitter. Note is going into the emitter. We take output from the collector as usual. So, it's going into the emitter, output is taking from the collector here. Base is small signal ground. Now, there's no capacitance between input and output. Which means what? I don't get Miller's effect. There's no capacitance here. So there's no capacitance that will appear at the input which is getting multiplied by the gain. So what we should do is, if we want to get rid of, let's say, this problem of Miller's effect, gain bandwidth product, maybe we should look in the direction of common base amplifier. What it is suggesting. Of course, if there's no capacitance between input and output, there's something else that goes wrong. Can anybody see what will go wrong here? Huh? Why will gain low? Okay.
So if you're not gaining anything over current, so if you make a panel of if you're getting a beta equal to 1.
Okay, alright. But you may still build up gain by choosing a large value of RC.
Then Again, we'll have problem voltage swings, right? RC very high.
Okay. There's another major problem. In a transistor, please keep in mind, I showed you a picture that when you look into the base, what do you see? Small signal. When you look into the base, what do you see? What appears? How does a transistor appear when you look into the base? It appears as a resistor of a value, R pi. Small signal, right? R pi. When you look into the collector, what does it appear as? R naught. R naught in parallel with. So this diagram, is very important. You internalize this particular picture here. Where is that small signal model here? Right, this picture here. Here, this one. This picture is simple, but internalize it that when you look into the base, you see an R pi. When you look at it from the collector, what you see is this doesn't show the whole picture. When you look at it, the collector, you see a current source, and in parallel, you see R naught. Okay, so that's other thing. And when you look into the emitter, what do you see? If RB is not there, you see R pi divided by beta. R pi divided by beta is what? 1 by GM. 1 by GM is what? Very, very small resistor. Okay. Now, in a common base amplifier, what did we do? Where did we connect the input? We connected the input to the emitter. When you look into the emitter, my source now is going into the emitter. When you look into the emitter, what do you see? You see a resistance which is 1 by GM. Very, very small resistance here. And when you make a voltage amplifier, what is it that you want? Very high resistance, input resistance here. So that is a major, major problem with this circuit here. The voltage, if you have some source resistance here, the entire voltage that you apply here will get dropped across the source. Very little will appear across the emitter. In fact, we'll see the gain. If I just look at the gain between this node and this node, the gain is large. You can get a gain as large as a common emitter. Gain is not a problem. Output resistance is not a problem. Bandwidth is good because there's no Miller's effect. But when I look from here, I see very small input resistance. Input resistance is negligible. It's just VT by IC, which is like 25 ohm. So that's the problem that I face with my common base amplifier. Okay. Another issue that we'll see later on, once we are done with common base amplifier, is that driving low impedance load is a problem for my common emitter amplifier. Low impedance load, which means RL here. So I've shown you a set of numbers, which with our background now we can easily calculate. These are numbers for let's say a common emitter amplifier with a load of 2.2K, biased at 3.4 milliamperes. And one can calculate that the power taken from the supply is 46 millivolt. Power taken from the supply will be 12 volt multiplied by current going in this branch and current going in this branch here. So sum of the two currents multiplied by voltage. That's the power here. Anyway, so voltage gain is 18.2. Here Rn is 2.7K. R naught, all that is given here. Note that we have left a little bit of emitter resistance unbypassed. And so we have a reasonable swing here, 2 volt. The power delivered to the load, we are assuming sinusoidal signal, is the voltage at the output, V0 square by 2 RL. So if we can get 2 volt here at the output, so we'll have 4 square divided by 2 square divided by 2 times RL here. RL is 2.2K, so we get load power. And efficiency of my amplifier is power delivered to the load divided by power I take from the supply is only 2%. Which means that out of all the power that I take from the supply, only 2% is useful and delivered to the load. That's it. So you can see here, it's very, very inefficient. And lower cutoff frequency is given here. Now, you can see what happens if I simply take this RL out, 2.2K, and replace it by a 22 ohm, a very low resistance here. And the moment I do that, if I take this amplifier, take RL of 2.2K out, substitute it by 22 ohms, my gain collapses to 0.36 here. My swing collapses. Obviously, the amplifier in its present form is not suitable for driving a 22 ohm resistor here. And you can see the output resistance is very high, 2.2K. So if I want to drive my 22 ohm load, these are the things that we'll see in detail later on. I'm just pointing out the problem. If I want to drive a 22 ohm load, which means that gain has collapsed, and gain, as all of you know, is ICQ. ICQ RC parallel RL. So what I need to do is I need to build up current. I need to increase the current in my amplifier here. ICQ RC parallel RL. If load resistance is 22 ohms, the factor here is 22 ohms. And if you want to build up gain, you have to build up ICQ. So note that what one has done is every resistor that you see, 2.2K, I've reduced every resistor by a factor of 100. Right? 2.2K. So I reduce it by a factor of 100, which means 22 ohms. So 22 ohms, all the resistors have been scaled by the same magnitude. Okay. And if you do that, gain doesn't go up to, for, you know, if you look at this particular circuit here, RL is 2.2K and all these resistors that you see here. Now, the idea is if I scale every resistor by a same factor, RL I've scaled by a factor of 100, RC scale by a factor of 100, all these if you scale by a factor of 100. If everything you scale by a factor of 100, you expect that ICQ should maybe increase by a factor of 100? Yes or no? ICQ should increase by a factor of 100. RC parallel RL has been decreased by a factor of 100. Resistors have been decreased by a factor of 100, so I would have expected gain to be roughly the same. I would have expected 18.2. But remember, in this circuit, there are some things which don't scale. So what I get here is, I get gain of only 4.2. I didn't get a gain of, these are based on simulation results, I get a gain of only 4.2. And the rest of them are given here. And the reason is, so far what we've been doing is, when we do gain calculation and input resistance and all that, we say, we neglect the effect of RBB. RBB that was there, we said in, you know, if you do a mid-frequency analysis, RBB is small and you can neglect its effect. But small with respect to R pi. So what happens is when gain is, when currents are small, let's say I have 1 milliampere current, R pi is 2.6 kilo. And then if I have a 100 ohm or a 200 ohm resistor here, maybe it doesn't matter that much. It's 1/10 of R pi here. But then when I increase the current by a factor of 100, then my R pi falls by a factor of 100. But RBB doesn't change. RBB is still the same. So now what happens is, RBB remained the same and R pi fell by a factor of 100. So earlier I could neglect the effect of RBB. Now I can't neglect the effect of RBB here. And now what you see here is the voltage that you apply gets significantly dropped across RBB and a lesser fraction appears here. And it's the fraction that appears here is the one that gets multiplied and appears at the output. So that's why simply scaling the resistors doesn't mean that, you know, your performance will remain the same. We increased the current by a factor of 100. Resistors all, we scaled it down. Gain didn't increase by the same amount here. Gain went up, but didn't go to 18 that we had expected. And that's because of the drop here. So what happens is when you are trying to drive low impedance loads here, you have to bias your transistor at a higher current. And then you have to be careful. You need a transistor with a lower base resistance also. The same transistor that you are using, let's say, at an input stage may not be very suitable at the output stage here. Okay, so you need to look at a transistor with a different characteristics here. So my common emitter amplifier has a problem that if I want to drive low load resistance, I'm requiring very high currents. I just showed you that if I have 22 ohms, I'm requiring a current of 247 milliamperes, very high currents. And the other one is my common emitter amplifier is very inefficient. Okay, so these are the two problems with my common emitter amplifier right now. And if you want an amplifier to drive a low impedance load here, you have to look for something else. Common emitter amplifier is not, you know, behaving in the manner that we want here. And the other problem is, you know, if, for example, you will have in general a multi-stage amplifier. So as I was telling you, to drive this low impedance load RL, what you will do is you'll raise the current level. And as you increase the current level, what happens is input resistance falls down. Because R pi is what? VT by ICQ. So input resistance falls down here. So as you try to drive this one, you'll increase the gain here. Its input resistance falls down. Now what happens is this acts as a load for the second stage. It acts as a you know, load for the second stage, and then second stage gets affected also. Because note that I have to build up gain here. and gain is nothing but ICQ, RC parallel RL. RL for this stage is 43 ohms. It also becomes very small. So the trouble with a common emitter amplifier, as you can see here, is that if you try to increase the gain, if you try to increase the current, then the input resistance falls down. And then input resistance falls down a lot, and then it affects my previous stages. So what we are looking for is a stage where you can drive low impedance load, and at the same time, you don't compromise on the input impedance. All right. So input impedance remains reasonable, but at the same time, you are able to build up voltage on a small resistance load here. And therefore, if input impedance remains high, then this particular stage it's easier to design that particular stage. Okay, if the load for this is high, and then one can build up gain and other things. So we are looking for a stage where, if you try to reduce the output resistance or drive more current into the load, you don't want input impedance to suffer. You want input impedance to still remain high here. So common emitter amplifier doesn't satisfy that. It doesn't satisfy that because all of you know AV times Rn by R0 is a constant. So as you try to reduce R0, Rn will also fall. Okay, so that's the problem for this thing here. So the issue is, if I'm looking for an amplifier at the output stage, what I want is, I want to drive low impedance load without requiring excessive bias current, without requiring, without being too inefficient, and without resulting in input impedance being too low. So that's one problem that we have to solve sometime down later on. The other one is gain for our common emitter amplifier is ICQ RC parallel RL divided by VT is directly dependent on temperature. That may not be something which is desirable. Gain being different at different temperatures is not something which you would like here. So that's a problem that you have to solve. One way of doing that is put a negative feedback. You put an RE here. Again, that RE, then what happens is you can analyze the circuit and show that AV is now approximately equal to minus RC parallel RL divided by RE, if RE is significant. Now you made gain independent of temperature, but then gain is very small also. If you calculate gain is large, dependent on temperature. Gain is small, independent of temperature. Okay, so that's the price that you have to pay. You use negative feedback, put RE here, and the gain then becomes independent of temperature, but it has a problem here. So what you do then is, if you want a gain which is high as well as independent of temperature, what you do is you build a multi-stage amplifier, build up a lot of gain, right? As I've been saying, what you could do is, this was, let's say originally this gain was 100. And what you do is, by putting RE, you reduce the gain to 10. It becomes temperature independent, but you have gain of only 10. So now the strategy is, if you still want 100, and temperature independent, what you do is you build a multi-stage amplifier, 3-stage amplifier. Let's say gain overall is 10,000. All right. Now what you do is you put negative feedback, reduce the gain back to 100, and you get a gain which is temperature independent. And all of you have seen this particular example. An op-amp with RF by R. Op-amp is a multi-stage amplifier with a very high gain, 10 to the power 4 or 10 to the power 5. It may be highly temperature dependent, the gain. But what you do is you sacrifice all of that gain, and the open loop gain and overall gain is RF by R, and RF by R, because it's a ratio of 2 resistors, is independent of temperature. Okay, so that's the strategy for getting a temperature independent gain. Build up lots of gain and then sacrifice it using negative feedback and obtain something which is temperature independent. Okay. So let me summarize then. For common emitter amplifier, we've seen that there's a trade-off here between gain, input, and output resistance limited by beta. And that's why you see that why we prefer transistors with beta as large as possible. If I have a beta of 200, my common emitter amplifier has greater capability in terms of obtaining larger gain, larger input resistance, and smaller output resistance here. So a high beta is a useful property here. We saw a supply budget here. Supply voltage is used to build up gain, is used to build up swing, and is used to provide stability here. So if you have a lower supply voltage here, then your ability to build up gain, swing, and stability suffers here. Okay, so that's one of the things here. We saw trade-offs between gain and lower cutoff frequency. We saw a trade-off between upper cutoff frequency and gain. So these are some of the important trade-offs that you are seeing here. Trade-off between input, output, and gain. This is a trade-off that you see here, limited by power supply. This is a trade-off between gain and swing, gain and lower cutoff frequency. This is a trade-off between gain and upper cutoff frequency. And key challenges, let me summarize. How do we get high gain without requiring large supply voltage? We look for a solution in this direction. Replace RC by a transistor here. So that's something that we'll have to deal with in future. Look at more on how to build an amplifier like this. Okay. This amplifier is called an amplifier with an active load. If I call this as a load element here, anything connected to the collector, this is passive, a resistor, and in this case, I have an active element, a transistor here, and so we call this amplifier common emitter amplifier with an active load. So that's a solution that one has to look for if one wants to build up gain without requiring large supply voltage. Okay. We identified a problem that if I want to build an amplifier on an IC, I can't have all these capacitors here. And so therefore we have to look for a amplifier which doesn't use capacitors to couple an input signal into the amplifier here or to take an output signal out from an amplifier. We need to avoid capacitors and we have to look for a new configuration where you can build up gain and all of that without requiring capacitors. So that's something to look at in the future. We saw that Miller's capacitance is a problem and we need a stage to overcome. I've already talked about, which we'll see in the next couple of minutes here. We need to look at common base as a solution to a Miller's effect problem here so that we can get high gain without suffering the drop in upper cutoff frequency. The other one was I talked about as an output stage, how do we build up sufficient voltage across a small load resistor in an efficient manner here. We'll see later on a solution for this problem will be a common collector stage. A common collector stage where you take the output from the emitter instead of the collector allows me to build up swing here across the load, is fairly linear, and and when you try to build up voltage across a very small load resistor, you do not suffer the input resistance dropping also. So a solution for this particular problem we'll see is a common collector here. And so it's pointing out the direction in which we have to move now in the remaining parts of the course. As a solution to this, we'll have to do common collector. As a solution to this, we have to go to common base amplifier. And then as a solution to this one, we'll have to move to another amplifier configuration here, eliminating the capacitances here, right? So let's start with